First, I would like to thank the organizers for invitation. So the title is up there. Maybe I should it's up there. So the title links several subjects. As you can see, if you see the Artin-Schelter regular algebras, this has some connection with non-commutative algebraic geometry. Then quantum groups, this is half algebra, non-commutative, non-co-commutative half algebras. Nakayama automorphism is defined by homological means. And also the words action means invariant theory. So it's connect several subjects. And this talk is based on joint work with my friends. So I list the names there. I'm not going to repeat their names. So today I will focus on one main theorem. So let me put the theorems here first. I will call this a homological identity. So the main theorem is this. It's too high. Oops, sorry. So let A be an AS regular algebra with Nakayama automorphism mu of A. And let K be a half algebra or quantum group, if you want, with bijective antipode called S, acting on A. Now, suppose the homological determinant of K coaction is D. I will explain all the terms after the theorem. Then we have this equation. I call it homological identity. Hi. Okay. Don't move. Where this is automorphism of K, it's just conjugation defined by conjugating this element D. And I will also define this later. This is the automorphism of K given by conjugating some matrix determined by this automorphism, Nakayama automorphism. Conjugating by the transpose of the corresponding matrix of Nakayama automorphism of A. So this is the main result I will talk about today. So maybe we just look at this equation. this homological identity. S is the antipode of K, so S squared is algebra automorphism of K. Then this is just the conjugation by D. I will explain what is D later. So this is automorphism of K. This is another automorphism of K. But these three automorphisms are coming from different places. First of all, this one coming from A. Nakayama automorphism of A is determined by A. But we will use this to define automorphism of K. But this is coming from K, that's clear. This D coming from the K action, K coaction on A. So this automorphism coming from both K and A. Okay, so we have three different automorphisms. Then somehow they are related. So this is the main result. After I explain all the terms, then I will give you some consequences. So basically, this homological identity is useful for solving the following questions. So let me put this one up. Oh, can you still see it? Right. So this is useful for solving the following, I would say, sample questions, because you can solve other questions. These are just examples. So again, let A be AS regular. Now, K here be a finite dimensional half algebra. In the theorem, the K could be infinite dimensional. But in the applications, I want K to be finite dimensional, half algebra, co-acting on A interfaithfully. I mean, just we just want faithful action. If not faithful, we can reduce to another action, right? This is me. So the question one. I don't know how many questions can I list. So under what hypotheses on A must K be semi-simple? SS for short for semi-simple. Question two. Under what hypotheses must K be a group? What I mean is that K is a group algebra. Okay. Question three, same hypotheses. Must K be a dual group? Or K is isomorphic to the dual of the group algebra? I guess I have a couple more, but let me put one more question here. Does every automorphism of A preserve the grading of A? I have a couple more here, but maybe I just want to stop here for the list of questions. Now, the last question is also related to a different question, which is to find the automorphism group of A, which is a very difficult question. And we have expert here, Jack Allen. He's working on this kind of question. I mean, he knows how hard it is to find the full automorphism group of some algebra. Okay? So somehow this homological identity is useful for solving all these questions. I mean, for certain cases, it's not, you cannot solve all the questions for all A and K, but for certain A and K, this is very useful. So this is what I want to say, I want to talk about today. All right. So the homological identity over there is kind of, you can solve different questions. So this is a very powerful tool for us. Now, I would say this is kind of, we know lots of very powerful equations like Euler formula or quadratic formula. So this is kind of plays this kind of role, but of course, this is less well known. So, so now I want to explain all the terms in the theorem. Let me start with the AS regular algebras, and of course, there's quite a few experts in this room working on AS regular algebras, but I still want to give a definition. So here's a, maybe before that, so let K be a base field. To be safe, let me put this one here. I don't think I need this, but maybe, you know, let me just put there. Okay, so definition. By the way, today I only consider connected graded AS regular algebras. The definition for AS regular algebras is defined for ungraded case. But a connected graded algebra, is called AS regular if we have three conditions. First of all, the global dimension is finite. Second, the X group from K to A is E0 or K. If I is not D, if I is D. Three, the GK dimension of A is finite. Now, I haven't given you the definition of GK dimension. This is just the growth of algebra. Or if you want, I can assume that A is Noetherian. That will be sufficient Noetherian. This will imply the finite GK dimension. In this case, are you talking about this zero? If I is not D is all zero. No. No. A is like a polynomial ring. Yeah. Right. I hope this is right. This is the definition. Okay, so let me give you some examples. I mean, definition is important, but examples are more important than definition. The commutative polynomial ring, this is the only the commutative AS regular algebra. So the AS regular algebra is a non-commutative version of the polynomial ring. Then you can deform this algebra. Skew polynomial ring is a AS regular algebra. And the relations are like xj, xi equal to pij, xi, xj. for all I less than j. Okay. Now, we have a u plus q Sn. Yesterday, I guess we see this algebra. Also, the quantum n by n matrices. Second n algebra. Down up algebra. Graded down up algebra. These are all AS regular. Then there is a classification of AS less equal to 3. This is done by Artin-Schelter, Tate, and Vandenberg. Okay. Then there's many, I'm not saying anything, many examples of AS bigger than or equal to 4. With no classification. There are many, many families. Even for global dimension 4, there's probably 50 families of algebras we can construct, but there's still no classification. So we have lots of examples. So I just want to mention one very nice conjecture here. It's not so much related to my talk, but the AS condition, this is Brown-Godot conjecture, which says that every Noetherian half algebra is AS. Okay? Can you see that? Sorry, maybe this is blocked. So every Noetherian half algebra satisfies condition 2. This is a very strong statement. So somehow the AS condition is just a generalization of half algebras. Maybe this is the wrong way to think about this. So hopefully I give you some examples of AS regular algebras. Maybe you get some idea. Now, I'm not going to define half algebra because we know what is half algebra things. But the next term is Nakayama Automorphism. Obviously, we know what is Nakayama Automorphism, but I still want to give a definition. Here. The classical case so let B be a finite dimensional Frobenius algebra. This means that we have an isomorphism between the dual of the B, the K-linear dual of B. This is a B module. Is isomorphic to this B module, the B module. As the left, the B module. This is the definition of Frobenius. Now, in this case, then the Nakayama automorphism B is, we use mu of B. This is automorphism of B such that, obviously this is bimodule, so we can look at the bimodule. This is isomorphic to B1 of mu. So this bimodule on the right side is twisted by this automorphism. So now what is the left and right multiplication here is like S times B times T is SB mu of T. Okay? So the left-hand side is just the usual multiplication. The right-hand side is twisted by this Nakayama automorphism. So this is a classical definition. Now, only for finite dimensional ones. But if we go back to the AS regular algebra, only finite dimensional AS regular algebra is just K, the trivial one. So all basically is always infinite dimensional. So we need to introduce a different, slightly different definition for the Nakayama automorphism. So Nakayama automorphism for AS regular algebra, which is again an automorphism of A, such that. So we want to have such a isomorphism, but now this is isomorphism here, A bimodule. A times A. This is A bimodule, this is also A bimodule. This is isomorphic to 0 if I is not D. And here it's A1 mu if I is D. Of course, this is not automatic from the definition. So this is the result, Z. So for AS regular algebra, you can always find the unique automorphism to make this is true. Okay, so this is that's the definition of Nakayama automorphism, which is very subtle invariant because it's not really computable. When D is not 0, it's not computable, basically. And A is called Calabi-Yau if the Nakayama automorphism is identity. This is the definition of Calabi-Yau algebra. Okay, so I give some examples here. In this case, this is Calabi-Yau. The Nakayama automorphism is identity. This is also Calabi-Yau. This is not in general. This is Calabi-Yau. I haven't defined this. Maybe I give you the definition of this Dahn algebra, then it will give you the Nakayama automorphism. So Dahn algebra. The graded case only is generated by D and U. D for down operation, used for up operation. D square U plus alpha DUD plus beta UD square equals 0, and DU square plus alpha UDU plus beta U square D equals 0. In this case, Nakayama automorphism sending D to the U. Let me see. Sorry, here's a minus U. So this, in this particular case, this is the Nakayama automorphism. Okay, and we can compute the other cases, other examples, but let me just do one. Yeah. So now, still, I guess I finished the first line, right? AS regular algebras, Nakayama automorphism. Now, second line, the bijective antipode that's clear. Then we have a homological determinant of the K action. So I need to explain this. What is homological determinant? Right. So let's see. I can only move one. Good, it's moving. You see, we're almost there. I need to explain the homological determinant. So now by the definition of AS regular algebra, number 2, then we have this vector space D of A, Ka. This is one-dimensional. Right? So I pick some basis, E. Then we have this one-dimensional. Now the K coacts on A, and also K coacts, K, the capital K, coacts on this trivial module. So K coacts on this vector space. What does that mean? This means that we have a co-module map then what do you mean? Then you can do this, right? What's the image of E? Image of E will be E times some K, D for D equal to inside the K. And we call this homological determinant. D is a homological determinant. Of course, there's a reason. If we start with a matrix, a GLN action on the vector space, if you go through this, then this agrees with the matrix determinant. But of course, here the A could be any AS regular algebra, K could be any half algebra coacts on this, and we still have this D here. So this is the homological codeterminant. Determinant, sorry. This is actually by Kirkman-Kutzmanowicz. Okay. Then let me see. So I have basically finished the first 2 lines. Right? I finished the first 2 lines. I need to explain the second, last 2 lines. So this is easy. This is already given definition is D inverse XD for all X in K. That's conjugation by D. I need to explain the last automorphism. So the consequence here is that D is a group-like element in K, so it's invertible. Yes. So I should say that D is a group-like element. Yeah. So now this is clear, right? I already explained this. Now finally, I need to explain the last automorphism. The last automorphism, I need to do some work. So first of all, the Nakayama automorphism is A to A, and also it's graded. I didn't say why it's graded, but by this result, this is graded. Then when this automorphism is graded, then we have a linear map from A1 to A1. Then I pick a basis. Pick any basis. A basis of A. Now, it follows from definition A1 is always finitely generated. Finite dimensional. It's not given, but it's a consequence of definition. Then the Nakayama automorphism can be written as using matrix, right? This maps to the summation of MIJBJ. So we have these coefficients. So M is this matrix. Then the M transpose, I use X for the M transpose. Then I use X bar. So this is my Xij. Sorry. X bar is the inverse of X. So I use this. Now we can define, use these scalars, we can define automorphism of K. So here's the definition. The mu of A tau. No, not quite yet. Sorry. Yeah. So one more line. Then, because K coacts on A, then we have a row from A. So I need to assume that. Sorry. Then we have row. This is J of Y, Ji for Y, Ji in K. Then I missed one hypothesis, which, the action should be interfaceful, which means that the K is generated by these elements as half algebra. In this case, then we can define this is the definition. X bar is yst x t j. Now, of course, probably you ask why this is automorphism of K. It's totally unclear. Okay? But the part of the result is says that this is automorphism of K and independent of the choice of this V. Okay? So if you pick a different V, you'll get the same automorphism. That's the point. So then I hope I explain all terms now. All right? We're almost there. We're done. Almost done. So now up at the top, I list some questions. I want to solve these questions by using this homological identity. Right, that's my goal. So the main application is in non-commutative invariant theory. So I want to give you some consequences. So first result. If A is Calabi-Yau and K coaction has either a central, let's just say central or trivial homological determinant, we call homological determinant trivial if this D is identity 1. Central means it's commutative with everything, right? In this case, then K is semi-simple. That's the first conclusion. I can even give you a proof. So if we look at this box here, the Nakayama Calabi-Yau means Nakayama automorphism is identity. So the last automorphism is identity. The first automorphism is identity because D is central. Then the S squared is identity. By Larson-Redford, K is semi-simple. Right? That's the proof. So after we have this homological identity, this has become trivial. Right? Yes. So for all these questions, K will be finite dimensional. Yeah. Otherwise, you only get S squared is identity, which is also a quite nice fact. But there is also conjecture. In the infinite dimensional case, this means that global dimension is finite. All right. So here the examples are like if A is commutative polynomial ring, the screen an algebra down UQ. I mean, in these cases, and if you have this situation, then K will be semi-simple in the feasible case. The second result is that if A, we only did a two-variable case, then semi-simple K must be a dual group. So if we have a semi-simple K to start with, if X on the polynomial ring in the feasible A, then K must be a dual group. It's a dual of the group algebra. So this is also in the same paper we proved. After we proved this, then this in the same paper. But then let me mention a result of Eddinghoff and Walton. So this was proved by my joint paper with Walton and Kenneth Cheng. So then she started thinking about other things, and she worked out a very nice result with Eddinghoff. Said if a semi-simple K coacts on a commutative domain, any commutative domain, then K is a dual group, which is a vast generalization of theorem 2. Right? Works for any commutative domain. All right, so let me mention two more results, then we stop. No. They use a different method, and yeah, their result is much better than theorem 2. Right. So if we have a special this skew polynomial ring to start with, then Pij, this is generic. Then this is not Calabi-Yau, but still we can use homological identity to get the following two results. The first one, K must be group algebra, and the G also abelian. Okay, that's first result. The second, and every automorphism of A is preserves the gradient. Now, of course, the second result is basically known because we can compute the automorphism group in this case. Right? But I just want to mention that the way we prove this is using this homological identity. It's not just try to find the automorphism group. One last thing. So let A be a graded down-up algebra. There is here we have a beta here. This beta. So suppose beta is not 1 or -1. Then first, K is a dual group. Must be a dual group. Second, if beta is not a root of 1, alpha is not 0, then K is also a group. G is abelian. 3, if beta is not root of 1, then every automorphism of A preserves the grading. So these are just the kind of, I guess, as a sample questions we can solve. My time's up, right? Thank you very much.
Any question?
Okay, I have a question about Artin-Schelter regular algebra of global dimension 3 and cubic, given by cubic relations. Do you have computed D, homological determinant?
This is an example, right?
Yeah.
This example. But the D is depend on the K action on A. So it depends on K and A. So you need to specify what is a K act on A. Then you can have a D.
Okay.
So for A, giving A, we cannot say what is a homological.
Okay, yes.
Yeah. But yes, it's computable.
But yes, I think about of a type A, or type A in classification. It is not
right, so if, for example, if you start from this A, right?
Yeah.
Then you need to tell me what is K, what is half algebra
okay.
K. After that,
But do you have any...
so we have lots of possible Ks. One project to classify all possible Ks which can co-act on A. I'm not saying we fix K. Just say if we have a K action on A, then we can define D.
Please, the microphone.
3D scanning, yes. Possible Ks are the groups, only group actions for finite dimensional ones.
So do you have any condition on the correction?
Please.
But do you have any requirements on the correction? Suppose the correction is trivial, and this identity is a pure identity on Hopf algebra, on the antipode.
Right, this identity is about automorphism on the K, Hopf algebra.
But, but suppose the correction is trivial, and there's nothing to do with the Nakayama automorphism of A. So then this identity becomes an impure identity on the Hopf algebra. Can you find such a group-like elements in the Hopf algebra?
All right. So first of all, this identity involves A and a K, right? So if there is no A.
Yeah, but here in the theorem you have no any requirement on the coaction.
No.
First for it?
If there is a coaction, then you have a homological identity.
Oh, yeah, okay.
Yeah.
I didn't see the, is interface for it?
Yeah, sorry, I should put interface for, interface for there.
Okay, then you have requirements.
Yeah, right.
Yeah. So then it's very close, like Galois correction.
Yes.
Possibly.
Yes. Right. May,
please. No, it's not all right.
Main idea of the proof, because Artin-Schelter regular algebras, K will co-act on the X group, XKK, right? But then the XKK is Frobenius algebra, so there is duality. So you use duality, then you'll get this. That's a short version of the proof.
Other question? No? So let's thank the speaker again.
Thank you.